Okay, welcome back. We're going to be looking at Unit 4, Lesson 3, graphing rational functions that are of this form. Grab the pen over here. This is a linear numerator over a linear denominator. Trust all is well with you and you're managing to cope. I'm going to go to Desmos first just so that we can see what would happen. So we can see right now currently this has a vertical asymptote and it has a horizontal asymptote. And I'm now going to change the value of A. So see how it was increasing the whole way? And at some point it makes a switch to decreasing all the way. And at this point right here, see how these, we'll call them, because we look at these as extreme points on a hyperbola. So I'm looking at these 2 points and notice how they're coming closer together and they meet and then we switch and we go the other way. So it starts out increasing. Those two extreme vertices, if you like, getting closer together till they meet, we form a line. There is a hole in the graph. Well, let me get back to the line just so that we can see. I think that was 1.8. Then we're going to have a hole in the graph. The hole isn't visible. We're going to have a hole right here. But you can't see it unless you zoomed in enough. Alright, so now let's take a closer look at some analysis. What kind of analysis is expected of you? And then an exemplar will be posted. So when will we have, actually I think what I'll do is I'm going to see what you remember about these. So what do you remember about when you have a vertical asymptote, when there's a vertical, where will their locations be? So I'm going to pause and let you think about that. All right, hopefully you did pause and then we'll take up the answers now. So we're going to expect to have vertical asymptotes whenever we divide by 0 here, as long as this isn't simultaneously 0, because that case would give us a hole. So noting, if first of all I said if C isn't 0, because if C is 0 then we're simply dividing by a constant and there definitely won't be a vertical asymptote. And I've also noted that AX plus B cannot be equal to CX plus D, or maybe I should note they can't be factors of each other. So let me just grab the pen, change that. CX plus D cannot be equal to some multiple that I'll call G of AX plus B. If that were the case, then those two factors will divide out and we will get a hole. Where will the asymptote be located? Wherever we have our 0 here. So wherever Cx plus D is 0, if Cx plus D is 0, then we're going to get that X is negative D over C. And remember, that will happen as long as C isn't 0, because if it were, we'd just be dividing by a constant. So really, we're kind of stretching or compressing the graph. And Cx plus D cannot be a multiple of Ax plus B. When will we have a horizontal asymptote? So again, we're noting that C can't be 0, because if C is 0, then again, we're just some kind of polynomial function. We are no longer rational. And I'm also noting again the same condition as above here. I'm going to note down here, because if Cx plus D is a multiple of Ax plus B, then again we're going to get a horizontal line with a hole in the graph. And that horizontal line will not count as an asymptote. Where is the asymptote going to be located? It's going to be located at A divided by C. That's kind of a review of what we did the previous day. And now I'll have you think about when will we have an x-intercept, where will it be located, when will there be a y-intercept, and where will it be located. So I'm going to recommend you pause now. So hopefully you did some pausing. We'll have an x-intercept as long as A isn't 0. Maybe I'll show you down here, it might make better sense here. If we do have an x-intercept, then the numerator has to be 0. And that will give me that Ax plus B equals 0. That gives me X is negative B over A. If A was 0, then this calculation here would not be defined. The other way to think about it is if A is 0, this doesn't appear here, and all we have is a B, there'd be no way for that numerator to be 0. When do we have a y-intercept? Well, I guess it would be the same logic, right? To have a y-intercept, what is the y-intercept? It is actually going to be, you're going to plug a 0 in for x. So when you plug a 0 in up here, you plug a 0 in up here, then we would be left with b over d. And b over d would be defined as long as d wasn't 0. So we'll have a y-intercept as long as d isn't 0. And the y-intercept will be b over d. And then we're just going to review how could you determine the behavior around the horizontal asymptote. This might be difficult to follow because we're not doing this in person, but what I've done here is I'm going to do a long division. We practiced that in class before we left. I'm going to divide cx plus d into ax plus b, and I'm going to need to multiply c by a over c. So c times a over c would just be a. That's how I'm getting my ax back. And that would be d times a all over c. And now when I subtract, those go, and I will get b minus dA over c. So what does that mean? That means I can now rewrite this as my quotient, which happens to be a over c, plus my remainder, which is there, out of my divisor. Again, I'm going to repeat that one more time because we've practiced this before. We can rewrite this as the quotient, which is right here, put a little q there, the quotient from up here, plus the remainder, which is right there, out of the divisor. Now the reason we want to do this, maybe I'm just going to go to a new slide because that's got a lot of arrows on it now. So let's home page. Let's go to a new slide. Let's go back here. I'm going to clear the ink off of this. Alright, so now why did we want to do that? Just want to click over there to get rid of that. Because this piece now is going to tend to 0 when x goes to infinity, because this is just going to be a number for simplicity. Let's suppose that was the number 2. Then we're either going to be looking at 2 over infinity, or we're going to be looking at 2 over negative infinity. And both of these are tending towards 0. This one towards 0 positively, but this one is tending towards 0 negatively. So I'm now going to, after that analysis, if I add a positive number to this, then I'm going to be approaching this from above. And if I add 0 negatively, I'm taking a small number away from this, so I'm going to approach a over c from below. So that's the basic gist of that. We will look at another example in greater detail. How do you determine the behavior around the vertical asymptote? So for the vertical asymptote, what I'm going to suggest, it'll be better when we look at an example, I'm actually going to factor out when we do the work. We're going to look at x plus b over a. I'm going to do that up here instead. Alright, so we're going to have been dividing it out like that. And then what will happen as we tend toward this number, right? I would plug that number into the numerator, and I'm going to get a number on the numerator. Let's suppose I get 3. But again, we'll look at an example. Then down here I have whatever this constant is. Let me just call that 4 for the sake of this example. And then what will happen as we plug into here, we are either going to be, x is either going to be, it's still going to be close to d over c, but if it is larger than d over c, then what will happen is this will approach 0 positively. If this happens to be smaller in magnitude than d over c, actually I wrote that backwards, let me erase that for a second. Alright, because we're approaching negative d over c. So if this is larger in magnitude than this, then we're going to be approaching 0 negatively. If x is now smaller in magnitude than d over c, then this has the larger magnitude. It's positive, so we're going to be approaching 0 positively. Then we'll be popping that value into here. And now we have positives, 2 positives, and a negative. This whole thing is negative. So this is going to be heading toward negative infinity. But I will walk you through that in an example. So that's the basic gist of that. All right, now here's our sort of not our exemplar or our anchor. This is kind of like our instructions on how to do it. So the first thing you're going to do in this graph is find the location of the vertical asymptotes and think about behavior around them. Determine the location of the horizontal asymptote. Think about behavior around it. Determine the location of all the intercepts. And then determine the positive and negative intervals. Then you should be stating the domain and range. And you should state the increasing and decreasing intervals. So let's jump to an example. I think what I'm going to do is pause this for a second. All right, so I just wanted to put some blinds up because it looks like there's so much going on there that you might find it distracting. So the vertical asymptote will occur whenever we're dividing by 0. So the first thing I'm going to suggest you do is factor. So I can common factor a 2 out. That gives me 2 times x minus 3. And I can common factor a 2 out of here and get 2 times x plus 2. Now the vertical asymptote will occur whenever this is 0. And the reason I factored was because I want to see, is it actually a vertical asymptote or is it a hole? Because if these two factors, this binomial factor and this one, if they divide out, we're going to end up with a hole in the graph. But in this case, they don't. So we're definitely going to have a vertical asymptote, and it will occur whenever x plus 2 is 0, and that's occurring at x is negative 2. And then the next thing we should be thinking about is we should be thinking about the behavior around them. So as x is going to negative 2 negatively, which is, this is sort of what I was talking about on this slide up here. Let's see if I can find it. Where I talked about, we would factor this, and then we would plug in here and we would try to decide which had the larger magnitude. Well, that's in action over here right now. So, I got that down at the bottom, so we'll show that as well. When I go to negative 2 negatively, so I'm going to plug the negative 2 into the numerator. 2 times negative 2 is negative 4. Negative 4 minus 6 is negative 10. So as x gets closer to negative 2, the numerator will get closer and closer to negative 10. And I just want to save that because the sign is important. As we approach negative 2, it doesn't matter. This guy is always going to stay 2, so I wrote that down. And then in here, I showed you I was doing a substitution. Negative 2 negatively, and there's the plus 2. So this is what x is. Now, if we are approaching negative 2 negatively, that's why I have the number line here, I just want you to see the magnitude of negative 2 is larger than the magnitude of positive 2, which means this value is going to be close to 0, but it will be negative, again, because if you are to the left of negative 2, which is what that means, move to the left of negative 2, your magnitude is slightly larger than 2. This has a magnitude exactly 2, so this will be larger, thus getting a number close to 0, but negative. Positive times a negative will still be a negative. And now we're negative 10 over 0 negatively. A negative divided by a negative will be a positive. And now this is going to be heading toward positive infinity. And off to the side, let me just do negative 10 over negative 0.000001, just to give you an idea of what we're talking about. When we say this is approaching 0 negatively, and then keep throwing more zeros in here. The more zeros you throw in front of this, the greater the magnitude of this will become. But it's going to become a very large positive number. Now, taking a look at this example. Now we are heading to negative 2 positively, which means we're heading to negative 2 from the right. Plugging a negative 2 in here again is still going to give me negative 2 minus 6, which is negative 10. This is not going to change. That's still approaching negative 10. This won't change. Now we're approaching negative 2 from the right, which now means we're sitting in here. So the magnitude of this x now will be less than 2. Close to 2, but less than 2. So this will have the larger magnitude. So close to 0, but positive. Now we have negative 10 divided by 0 positively. Again, because that's a positive, times this positive gives me 0 positively, and a negative divided by a positive is negative, so this is going to be heading to negative infinity. And then I just wanted to summarize again from the graph here. If you approach -2 from the left, the magnitude of x is going to be greater than 2. If you approach -2, there's a typo there. Let me just correct that. That should say positively, because we are approaching -2 from the right here. As you approach -2 from the right, the magnitude of x will be, that's what happens when I copy and paste. That should say smaller. So you have to forgive my errors. I don't have an editor editing my work. I just did a copy and paste. So this should say, as x goes to -2 positively, the magnitude of x will be smaller than 2, which is why we got a positive back there. All right, so there's our analysis. As we head to -2 negatively, key points that are important, then the function is going toward positive infinity. As we head to -2 positively, the function is heading to negative infinity. And maybe I'm just going to add a slide to show you what that would mean. So if I'm going to graph this, we said we have an asymptote at -2. And we'll just come back here just so that we can see what we said. When we approach -2 from the left, we go to positive infinity. When we approach -2 from the right, we go to negative infinity. So coming back over here, I'm approaching from the left, we should be going to positive infinity. Approaching from the right, we should be going to negative infinity. So that's what that part of our graph would look like. All right, now we're trying to figure out horizontal asymptotes. So we're going to end up with a horizontal asymptote. All right, the shortcut I used here was just to divide the leading coefficients. But now I want to show you a couple of different ways and why that might make sense. So if you like to memorize things, if you divide A over C, that will be the location of the horizontal asymptote. We summarized that earlier in the class. Two ways to think about this. One, because both of these are linear, I should be able to break this up, -6, to create +4, which is what I did here. 2x plus 4 minus 10, that's -6. That allows me to split this into 2x plus 4 over 2x plus 4 plus -10 over 2x plus 4, and that's going to give me 1 plus -10 over 2x plus 4. And that's an alternative to long division. If I do the long division, then 2x plus 4 is going into 2x minus 6. 2x goes into 2x once. 1 times 2x plus 4 is 2x plus 4, and when I subtract, I get my -10. And again, I'm going to, let's see if we can get that pen. The quotient goes here, the remainder goes here, the divisor goes there. So I'm going to get the same answer again, regardless of how we slice that. All right, now we're going to think about behaviors, because you have to analyze the behaviors now. So when you go to infinity, I mentioned earlier, I think I just want to erase that ink off that so we can see it now. Whoop. The reason we want it to be written in this form is because I'm guaranteed that this piece will tend towards 0, because the degree of the denominator exceeds the degree of the numerator. So when x is going to infinity, h at x is going to be going to 1 plus, there's the -10 from the numerator. Now if you multiply infinity by 2 and add 4, you're still at positive infinity. Now -10 divided by positive infinity will be a number that's very close to 0 but negative. So now what we're going to be doing to 1 is we're going to be adding a number that's close to 0 but negative, which means we are going to be a number just under 1. So we put 1 negatively just to show that we are below 1. When we head toward negative infinity, we're going to get our 1 plus, there's the -10, but now 2 times negative infinity plus 4 is still going to be negative infinity. And a negative divided by a negative is going to be a positive, so this number is very close to 0 but positive. When you add a number close to 0 but positive to 1, you'll get a number that's just a little bit larger than 1. So what's happening with regard to our summary then? As x goes to infinity, h at x is going to 1 negatively. and that's from up here. And as x goes to negative infinity, h at x is going to 1 positively, and that was that analysis there. All right, so we've done our vertical asymptote analysis, our horizontal asymptote analysis, and now we're going to look for intercepts. So if you want to find the x-intercept, then you're looking for when this is 0. So let's see if I can make that 0. And again, we had already factored this earlier. 2 times x minus 3 over 2 times x plus 4. The reason I'm showing you that now is just because this is 0 doesn't guarantee there will be an x-intercept. If we get 0 and the other one is, the denominator is also 0, then we will not get an x-intercept. We're going to end up with a hole in the graph here. So 2x minus 6 is 0 when x is 3. And when x is 3, the denominator is not also 0. So we're definitely going to have an x-intercept at 3, 0. When I'm trying to find the y-intercept, what I'm going to do is I'm really going to be plugging in 0 here and here. So let's get rid of that so I can have some space to work. So we'd be looking at 2 times 0 minus 6 over 2 times 0 plus 4. That's going to give us negative 6 over 4. So that's where that came from. All right, next slide. After you've done all of the analysis, I did ask for the positive and negative intervals. If you want to cheat, one way to do that would be to simply look at the graph. Another way to do it is to create interval charts. Now, in our interval chart, you are used to putting this one in because that's where the zeros are, right? But we also now need to include where the asymptotes are, because a function could change sign. So we could have a vertical asymptote, let's say right here. And look, I was positive over here, and then I was negative there. So we could change sign as we cross a vertical asymptote. So in our list, in addition to having the zeros, we'll also have the locations of the asymptotes. So we have an asymptote at negative 2. We have a 0 at 3. So starting from negative infinity, stopping at negative 2. From negative 2 to positive 3, and from 3 to infinity, writing everything in ascending order. X plus 2, that's the location of the vertical asymptote. And this one here is the location of the 0. It will be important to include these numbers in out front rather than the just the factors, because if this was negative and this was positive, that would be altering our signs over here. So I've written the whole thing in here. Between negative infinity and negative 2, both of these are negative. Between negative 2 and 3, this factor becomes positive. That one is still negative. Between 3 and from 3 to infinity, both factors are positive. A negative times a negative is a positive times a negative is a negative, a positive times a positive is a positive. So in summary, our function h at x will be positive on negative infinity, negative 2. It will also be positive on 3 to infinity. So there's the 3 to infinity, and there's the negative 2 to infinity. And then our function h at x is going to be negative on the interval negative 2 to 3, and I've summarized that one over there. All right, then the next thing you would do is you would draw any asymptotes, and then you would plot your intercepts. So we've already determined that we have a vertical asymptote at x equals negative 2. We have a horizontal asymptote at y equals 1. We have our x-intercept at 3, and we found our y-intercept to be negative 3/2, and I'm plotting that right there. So on your graph, you would plot all of those points, and then you would use your end behavior. So let me just show you back here where we had all of those. All right, that one we already discussed. So -2 negatively, we're going to positive infinity. -2 from the right, we're going to negative infinity. So let me just show you back to this graph here what that would mean. That would mean we've got something sitting in right here, and we've got something sitting right there. And now let's jump back just to see how we were approaching 1. That was on this slide. So when we go to positive infinity, we're under 1. When we go to negative infinity, we're above 1. So positive infinity, we're under 1. Negative infinity, we're above 1. And that works nice because it will allow me to sort of finish off the curve. And that's working with the other calculations I made. I'm now able to finish off the curve. So after I've drawn the asymptotes, I'm going to use the rest of the analysis to finish off the rest of the sketch. And that's what the sketch will look like. And I have highlighted for you in blue, that's the intervals on which the curve is positive. In red, that's the interval on which the curve is negative. Then after that's done, you should be stating the intervals of increase, decrease, domain, and range. So from over here, we can see that the domain is all real numbers but -2. We are increasing from negative infinity to -2. Then we're increasing from -2 to negative infinity. We have to separate this into 2 separate intervals. Remember, using the round brackets to indicate that's not included. A square bracket says you should include it. We are not increasing at -2. The function's not defined there. Our positive intervals were right here, from negative infinity to -2, and from 3 to infinity. We had our vertical asymptote right here, which was at x equals -2. We have our x-intercept right here of 3. Our range, we're going to hit all real numbers except this value right here, and that's 1. That's where our asymptote is. So all real numbers but 1. This interval is never decreasing. It is always increasing. The interval is negative on -2 to 3, that part in red there. The horizontal asymptote is located right here at y equals 1. And our y-intercept was right there at -1.5. So that summarizes what you need to do when you're going to create a sketch of a rational function. I have, let me see if I can find that. I'm just going to pause for a sec. All right, so I have posted a graph anchor here. And this anchor is just showing you what you need to do. Find the vertical asymptotes, identify the behavior around them, and notice how when I'm identifying the behavior around them, in factored form, I'm allowing myself to figure out whether x has a magnitude greater or larger than 2. And again, we said because you're to the left of 2, then this has the larger magnitude, that's 0 negatively. And when I look at the combination of positives and negatives, this is negative, so I'm heading to negative infinity. When I head to -2 positively, 2 has the larger magnitude, so this becomes positive. To find the end behavior asymptote, there was the long division, but I also said, well, this one's going to be a bit harder to split it up, but it doesn't mean we can't do it. But this one would be harder to use that other technique I showed you, because I would then have to take a 3 out of there, -3, and write that as 2x minus 10/3. That's how I'm going to get my 6x plus 10. And then we have this being divided by 2x plus 4. And then I could try and split this up to get a plus 4. But I think that would be harder here, so maybe it's just better to do our long division. And in our long division, we can now see that we can rewrite this as -3 plus 22 over 2x plus 4. Again, trying to figure out the behavior on the ends. We're really going to plug a positive infinity in here and see that when we do, well, actually this one was negative infinity, so I'm plugging in negative infinity, and I get a positive divided by a negative, close to 0 but negative, approaching -3 from below. Here I'm heading toward positive infinity, plugging that in. All of this is going to become positive, so it's close to 0 but positive, so I'm approaching -3 from above. Find the location of the y-intercept, the x-intercept, and then uses all of that information to sketch the curve. The only thing I didn't do was I didn't answer all of those questions there. One last thing to show you. All right, I had to start a new recording because I accidentally stopped instead of pausing. So I want to show you here where we had your turn over here. So it's your turn to do some practice. What I've done is I converted these all to GSP Web Sketch. So now you can click on here, and it's going to open something up here. And you can imagine doing all of the work. You want to check your answers, it'll show you your answers. You can check the graph, it'll show you the graph. There's the extra questions you answer later: domain, range, intervals of increase, decrease, positivity, negativity, etc. You can check those answers. Navigation through this, you can use next page and previous page. Just want to show you when we get to the last page. You can change this on your own just by clicking in here, change that to another number. This works very well, except in the case where you're going to get a hole in the graph. So when you get a hole in the graph, what will happen is it will display it properly. Let me just quickly change this to 2. Then change this down here to 5. All right, so now we should have a hole in the graph. So it displays the graph, but it doesn't display the hole in the graph. And then it's going to have trouble giving you the correct answers here. These answers should be correct. Actually, no, that's not right, because you're not increasing anywhere. You are positive everywhere, so this one is right, but that one's not right because it's not increasing everywhere. It's not decreasing at all. And these are wrong. So this works great, but I'm going to suggest don't use this when there's a hole in the graph, because there are issues with the answer being correct, and it was too difficult to figure out the programming. All right, so that's going to conclude this lesson. And since I'm trying to be a better YouTuber, don't forget to like and subscribe. And then I guess hit the bell icon for further notifications. And Mr. Ciprietti told me I should say it this way. Don't forget to smash the like button. And I'm adding with all the mass times acceleration that you can muster. Enjoy the rest of your day. See you next lesson.